The white line painted across the rock face at the mouth of the Fraser River Canyon in British Columbia was meant to mark the historic low-water threshold of the 1930s Dust Bowl. On the morning of July 18, 2026, the water level passed 3 meters below that mark. Across Western Canada, 3 separate monitoring systems registered anomalous readings within minutes of each other. At 2:14 Pacific Daylight Time, an automated sensor on the South Saskatchewan River below Lake Diefenbaker registered a discharge velocity drop to levels not seen since the reservoir was first impounded in 1967. At 2:17, an Ocean Networks Canada seafloor node off Vancouver Island recorded an abrupt 0.8 degree rise in bottom water temperatures along the continental shelf. And at 2:22, a meteorological array in the interior of British Columbia clocked an overnight low temperature of 27.4 degrees Celsius. 3 separate agencies, Natural Resources Canada, Environment and Climate Change Canada, and the Geological Survey of Canada, were looking at 3 different physical domains, but they were looking at 3 readings of a single atmospheric engine. The headline framing calls this a summer heat wave. That framing is wrong, and correcting it is the only way to understand what is happening right now to tens of millions of people across North America. A heat wave is a temporary weather spike, an uncomfortable afternoon peak that arrives, passes, and allows the surrounding environment to reset. What is sitting over the western half of the continent right now is a persistent planetary-scale blocking high-pressure system, a stagnant atmospheric dome that has locked itself in place, capping the lower atmosphere, compressing the air beneath it through intense adiabatic heating, and systematically stripping the night of its ability to cool. The newsfeed sells daytime records. 41 degrees in interior valleys, broken high-temperature marks from Calgary to the Fraser Canyon. But the daytime peak is not the engine of this crisis. The true danger, the metric that determines whether human bodies survive, is what happens after midnight. In cities where a normal July night should bring relief down to 14 or 15 degrees Celsius, the overnight low hangs suspended at 26, 27, and 28 degrees. The air is saturated with moisture, locked in place by high dew points that prevent evaporative cooling. The human body, which relies on those overnight hours to shed the thermal burden accumulated during the day, gets zero recovery window. To understand why overnight lows matter most, look at the human body as a thermodynamic machine. Under normal conditions, core physiology generates heat through metabolic function, maintaining a baseline near 37 degrees Celsius. When ambient temperatures drop at night, a passive temperature gradient forms between skin and surrounding air, allowing the cardiovascular system to lower its workload, kidneys to normalize fluid balance, and core temperature to dip during sleep. But when overnight air stays above 25 degrees, passive transfer halts. The cardiovascular system maintains high-volume blood flow to the skin all night long. The kidneys fight fluid and electrolyte depletion from continuous sweating. The physiological debt is rolled over into the next morning. When a second, third, and fourth day of 40-degree heat arrives on an unrecovered system, the burden compounds exponentially. This compounding effect is why excess mortality data spikes during sustained blocking events. In the 2-week period ending July 1st, official statistics recorded a 39% surge in excess deaths across affected regions. Quiet deaths occurring in top-floor apartments, unair-conditioned homes, and urban concrete pockets that retain heat long after sunset. As this blocking dome expands eastward across the prairies toward the Great Lakes, it moves into communities where residential infrastructure is built explicitly for heat retention during sub-zero winters, not heat dissipation in midsummer. The coming days will test the limits of North American grid stability and human physiological endurance. Keep your eyes on 3 specific indicators over the next 48 hours. Whether overnight dew points remain anchored above 20 degrees, whether Environment and Climate Change Canada elevates regional heat warnings to emergency advisories, and whether streamflow velocities on major glacier-fed rivers drop below historical minimums. What is the single atmospheric mechanism locking this dome in place, and how much further will it push? On July 28, 1936, standard mercury thermometers inside the Stevenson screen at the Dominion Observatory in Ottawa registered an afternoon maximum temperature of 37.8 degrees Celsius. It was the peak of a 6-day heat event that killed over 1,100 people across Ontario and Manitoba. For 85 years, that 1936 event remained the absolute benchmark, the structural baseline against which civil defense plans, municipal building codes, and agricultural risk models in Canadian history were calibrated. But on June 29, 2021, at the Weather Monitoring Station in Lytton, British Columbia, 45 kilometers south of Lillooet, digital sensors recorded 49.6 degrees Celsius. That single reading shattered the 1936 benchmark by 11.8 degrees. 24 hours later, the town of Lytton was completely consumed by wildfire. Popular media coverage described Lytton as a freak accident, a black swan event of localized bad luck. But that sensational framing misrepresents the physics. What happened in 2021, and what recurs right now across Western and Central Canada, is not a localized fluke. It is a fundamental realignment of the atmospheric baseline. The statistical envelope that governed North American climate behavior for the entire 20th century has collapsed. Historical records compiled by the Geological Survey of Canada and the Meteorological Service of Canada since 1871 were built on the assumption that extreme events fluctuate within a stable, bounded range. That baseline assumption is now completely obsolete. To grasp how far outside historical norms current conditions sit, look at how the Northern Hemisphere's atmospheric circulation previously functioned. Historically, the polar jet stream, a high-altitude ribbon of fast-moving air flowing 11 kilometers above the surface, acted as a sharp thermal barrier. Driven by the steep temperature contrast between the frozen Arctic and temperate mid-latitudes, this jet stream moved rapidly from west to east in a tight, relatively straight path. It carried low-pressure weather systems across the Pacific, dumping precipitation over the coast mountains, filling BC hydro reservoirs, and sweeping cool marine air across interior plateaus every 3 to 5 days. Under this historical baseline, heat events occurred when the jet stream developed moderate north-south meanders known as Rossby waves. A ridge of high pressure pushed warm air northward into the Canadian prairies, driving afternoon temperatures into the low 30s. But because the temperature gradient between the equator and pole was strong, the jet stream moved fast. It pushed the high-pressure ridge eastward toward Atlantic Canada within 48 to 72 hours. Nights remained cool, typically dropping to 12 or 14 degrees Celsius because dry prairie air efficiently radiated heat into the upper atmosphere after sunset. The land cooled, buildings shed thermal loads, and the population experienced minimal physiological stress. That mechanical balance depended entirely on a cold Arctic. Over the past 4 decades, Arctic amplification, rapid warming of the northern polar region driven by sea ice loss and albedo decay, has reduced the temperature differential between pole and equator by nearly 30%. When that thermal gradient weakens, the jet stream loses momentum. Instead of a tight, fast-moving belt of air, the jet stream becomes slow, wavy, and prone to extreme distortion. It stretches into massive, high-amplitude loops that stall completely across the continent for weeks at a time. When one of these distorted loops stalls, it creates what atmospheric scientists call a blocking, high-pressure omega block, named for its resemblance to the Greek letter omega. Under an omega block, warm air from southern latitudes is drawn deep into the Pacific Northwest and the Canadian interior. As the high-pressure system anchors itself over the landmass, it sinks. Sinking air compresses, and as it compresses, it heats up at approximately 10 degrees Celsius per kilometer of descent, a process known as adiabatic compression. This creates a massive atmospheric lid, or heat dome. The dome suppresses cloud formation, allowing maximum solar radiation to bake the surface uninterrupted for 16 hours a day. The ground dries out, eliminating soil moisture. Without soil moisture, solar energy can no longer be converted into latent heat through evaporation. Instead, 100% of the sun's energy goes directly into sensible heating, warming the air directly above the ground. At night, the high-pressure cap locks that superheated air near the surface, while elevated moisture levels trap outgoing radiation. When Environment and Climate Change Canada deployed meteorological balloons over Edmonton and Kamloops during baseline breaking events, radiosonde instruments recorded upper atmosphere temperatures at 85 kilopascals that were 5 standard deviations above 1981-2010 climate normals. In statistical terms, 5 standard deviations represents an event so rare that in an undisturbed climate system, it would occur less than once every 7,000 years. Yet today, these exact 5 sigma blocking patterns manifest repeatedly across British Columbia, Alberta, Saskatchewan, and Ontario. Infrastructure engineered under the old baseline, concrete highways that buckle at 40 degrees, power distribution networks designed for winter peak loads rather than summer cooling demand, and unair-conditioned urban housing stocks faces a climate reality it was never designed to endure. To evaluate where this crisis moves next, watch 3 vital monitoring indicators over the coming days. First, whether 500 millibar geopotential height contours over the Canadian prairies remain stationary above 5,900 meters. Second, whether nighttime low water flow rates on the Bow River through Calgary drop below 15 cubic meters per second. And third, whether the Canadian Wildland Fire Information System elevates the national preparedness level to its maximum setting of level 5. Is this the new permanent baseline, or just the beginning of a larger atmospheric shift? On a digital control screen at the Canadian Meteorological Centre in Dorval, Quebec, a single atmospheric variable flipped from blue to dark red at 3:45 Eastern Daylight Time. It was not peak surface temperature, it was dew point temperature, recorded by an automated weather station near Lake Diefenbaker, Saskatchewan, registering 22.4 degrees Celsius. In standard forecasting software used for decades across North America, a dew point above 20 degrees in the Canadian prairies was treated as an operational impossibility, an instrument glitch to be flagged and filtered out. But within 45 minutes, 16 adjacent stations across Alberta and Manitoba confirmed the exact same threshold. The air mass moving across the interior continent was no longer simply hot, it was saturated. Sensationalized media reports immediately blamed the unfolding emergency on sudden solar spikes or transient jet stream anomalies. That framing is misleading. The true breaking point, and the actual mechanical failure underway, is a fundamental breakdown in thermodynamic dissipation. The accurate story is not about how hot the sun gets at noon, it is about how the lower atmosphere loses its physical ability to cool after dark. When you understand the precise vapor pressure mechanics that govern nighttime heat radiation, the true scale of this continental threat becomes undeniable. Under standard meteorological conditions, the land surface absorbs shortwave solar radiation throughout the day. After sunset, the surface attempts to shed that accumulated thermal energy by emitting long-wave infrared radiation back into space. If the air mass above the ground is dry, meaning it has a low dew point, that infrared radiation travels upward through the atmospheric column with minimal obstruction. Surface air drops rapidly by 15 to 20 degrees Celsius before dawn. This nocturnal drop is the primary cooling mechanism of the mid-latitude climate system. However, when a stationary blocking high-pressure system draws moist air masses north into the continental interior, vapor pressure dynamics change entirely. Water vapor is the most powerful greenhouse gas in the lower atmosphere. When dew points rise above 20 degrees Celsius, the concentration of water molecules in the boundary layer reaches a saturation threshold, where air becomes optically thick to long-wave infrared radiation. Instead of escaping into space, heat emitted by the ground is absorbed by moisture in the lowest 300 meters of the air column and re-radiated straight back down to the surface. This radiative trap creates a hard physical floor beneath nighttime temperatures. An air mass cannot cool below its dew point without triggering condensation, which releases latent heat of vaporization directly back into the air, further halting any temperature drop. When the dew point sits at 22 degrees, overnight temperatures are physically locked above that number. The nighttime cooling engine effectively ceases to operate. The human body experiences this atmospheric breakdown as a physiological failure cascade. To shed internal heat, your core relies on 2 main pathways: convective cooling into surrounding air and evaporative cooling through sweat. Convective cooling requires ambient air to be significantly cooler than your skin temperature of 35 degrees Celsius. Evaporative cooling requires a steep vapor pressure gradient between wet skin and surrounding air. When ambient overnight temperatures remain at 27 degrees and humidity levels push dew points above 22 degrees, both cooling pathways fail simultaneously. Sweat forms on the skin, but because surrounding air is saturated, it cannot evaporate. The sweat sits there, providing zero thermal relief while draining vital fluids and electrolytes from your circulatory system. To keep core temperature at 37 degrees, your nervous system triggers extreme cutaneous vasodilation, redirecting vast volumes of blood from internal organs outward to the skin. This forces your heart to pump at elevated rates for hours without rest, dramatically escalating cardiovascular workload during nocturnal hours reserved for physiological recovery. At the same time, kidneys work at maximum capacity to manage severe fluid imbalances. For elderly individuals or those with underlying cardiac conditions, this uninterrupted nocturnal strain causes sudden vascular collapse, acute renal failure, and fatal heat stroke. This physical failure was verified in real time by the Canadian Hazards Information Service and Environment and Climate Change Canada, using ground-based radiometer networks and Doppler LiDAR profilers. Data confirmed that the lower atmospheric planetary boundary layer remained completely unstratified overnight, maintaining a continuous heat flux directed downward into the urban canopy. Historical predictive models, which relied on standard Gaussian temperature decay curves after sunset, completely failed to project mortality spikes because they assumed a nighttime thermal drop that no longer existed. To track how rapidly this thermodynamic trap compounds across the continent, watch three crucial technical metrics over the next 24 hours. First, whether automated weather stations in southern Ontario and Quebec report midnight dew points exceeding 21 degrees Celsius. Second, whether regional health authorities trigger Level 3 mass casualty protocols for cardiovascular distress. And third, whether upper air radiosonde launches at Stony Plain, Alberta, show a persistent subsidence inversion below 800 hectopascals. If these three signatures persist, nighttime cooling failure will expand into the most heavily populated corridors of North America. What happens when this thermal debt hits our urban infrastructure? At 14:15 Pacific Daylight Time on July 21, 2026, a high-voltage circuit breaker tripped at the Nicola substation near Merritt, British Columbia, knocking out a key 500 kilovolt transmission line connecting interior hydro generation to the coast. The cause was not a storm, a lightning strike, or a fallen tree. The cause was thermal expansion. Continuous, unremitting heat caused heavy aluminum conductor cables to expand, sag 5 meters below design clearance, and arc directly into dry brush along the right-of-way. Within 12 minutes, automated load-shedding software executed emergency brownouts across 42 municipal grids from Kamloops to Vancouver. The grid did not fail because of a sudden spike in demand. It failed because physical materials that transmit electricity across this continent are reaching structural thermal limits. Mainstream news outlets reported the outage as a routine equipment glitch during peak summer usage. That headline framing obscures a far more dangerous reality. The real story is not that a power line sagged. It is that critical physical infrastructure underpinning Canadian society, transmission lines, rail corridors, municipal water intakes, and agricultural supply chains, was engineered for an atmospheric baseline that no longer exists. When sustained heat prevents nighttime cooling, infrastructure systems lose their physical ability to shed thermal strain, cascading into structural failures across every major economic sector. Consider transportation networks moving $500 million in freight through the Cordillera every single day. Along Canadian National and Canadian Pacific Kansas City main lines running through the Fraser Canyon, continuous rail temperatures exceeding 50 degrees Celsius trigger thermal expansion stresses known as sun kinks. Steel rails expand linearly, buckle sideways under tension, and force immediate speed restrictions from 90 kilometers per hour down to less than 20. Train lengths are cut in half to prevent derailments. At the Port of Vancouver, containerized cargo piles up on docks as rail throughput collapses by 60%. That delay ripples across 4 provinces within 72 hours, disrupting agricultural exports, industrial supply lines, and interprovincial food distribution. On asphalt highways like the Trans-Canada and Highway 5 through the Coquihalla Pass, binder bitumen softens under continuous 40-degree ambient exposure. Heavy transport trucks shear pavement surfaces, creating deep rutting and thermal blowups, where concrete slabs expand against expansion joints and shatter upward. Main transportation arteries connecting British Columbia to the rest of Canada are reduced to single-lane controlled bottlenecks, adding hours to critical supply routes. The water infrastructure crisis is even more severe. In southern Alberta, where the Bow and Oldman rivers support over 600,000 hectares of irrigated farmland, an agricultural area larger than Prince Edward Island, glacier melt from the Columbia Icefield and Athabasca Glacier initially surges during early heat, then plummets as snowpacks vanish weeks ahead of schedule. Reservoir storage at Lake Diefenbaker and along the South Saskatchewan River system drops toward intake elevations. When water levels pass below primary municipal intakes, pumps cavitate and fail. Municipalities are forced to issue emergency water restrictions, shutting down industrial processing plants and halting agricultural irrigation during the peak growing window. Agriculture across prairie provinces faces a compounding disaster. Soil moisture deficits deepen exponentially as evapotranspiration rates exceed 25 millimeters per week. Wheat, canola, and barley crops enter thermal stress, aborting flowering and shedding yield potential day after day. Financial losses across Western Canada are measured in billions of Canadian dollars, dwarfing historic drought damages of 2002 and 2021. Simultaneously, the Canadian Wildland Fire Information System records explosive fire behavior across northern forests. Desiccated fuel beds ignite instantly from dry lightning strikes. The resulting smoke plumes, carrying microscopic particulate matter, cover millions of square kilometers, an area larger than Ontario and Quebec combined. Smoke caps urban centers, reflecting sunlight during the day but trapping infrared heat at night, further locking elevated overnight temperatures into dense concrete cities where unair-conditioned apartment towers become thermal traps for vulnerable residents. Alert-ready emergency notifications flash on millions of mobile screens, advising residents to seek cooling centers as public health networks trigger mass casualty protocols. To understand where this infrastructure crisis escalates next, monitor 3 vital operational benchmarks over the next 48 hours. First, whether BC Hydro and Hydro-Quebec issue formal grid emergency advisories due to line sag capacity limits. Second, whether rail speed restrictions remain enforced along primary mountain passes. And third, whether Public Safety Canada activates interprovincial assistance agreements to deploy emergency power generators to municipal water facilities. If these 3 indicators flash red, infrastructure strain will transition into structural systemic disruption. How much longer can our built environment hold before the entire network breaks? On August 2, 2026, at 1:30 Pacific Daylight Time, a single sensor log from the automated monitoring site at Lytton, British Columbia, registered an ambient air temperature of 26.8 degrees Celsius. Exactly 5 years earlier, after the catastrophic 2021 heat dome incinerated 90% of that same town, emergency planners argued that such conditions represented a once-in-a-millennium anomaly. Yet here on the exact same ground, instruments logged nearly identical thermodynamic values for the second time in half a decade. The system did not reset. The old baseline never returned. Standard media summaries frame this as a temporary climate surge, suggesting that once the current high-pressure ridge breaks, normal summer conditions will automatically re-establish themselves. That framing fundamentally misrepresents the physics. What makes this crisis deeply sobering is that atmospheric dynamics governing North American weather have crossed a structural threshold. The blocking high anchored over the continent will eventually dissolve, as every atmospheric pattern eventually must. But the warmer background baseline onto which the next blocking high will settle is now permanently elevated. Data from Environment and Climate Change Canada, Natural Resources Canada, and the Copernicus Climate Change Service confirm that global mean surface temperatures have maintained a sustained elevation above the 1.5 degree threshold for over 12 consecutive months. Oceanic heat content in the North Pacific and Atlantic basins has reached the highest absolute values ever measured by autonomous Argo profiling floats. This thermal energy continuously feeds moisture into mid-latitude air masses, ensuring that when blocking ridges form, they do so with higher dew points, greater optical thickness to long-wave infrared radiation, and elevated physical resistance to jet stream displacement. What remains unresolved is the precise tipping point for the polar jet stream itself. Atmospheric physicists at the Geological Survey of Canada and international academic institutions are debating whether the jet stream's increased wave amplitude represents a smooth, linear response to Arctic warming or a non-linear regime shift, a point of no return where persistent blocking patterns become the primary atmospheric mode of the Northern Hemisphere rather than an occasional exception. If the system has entered a new regime, multi-week heat domes that once occurred decades apart could become regular, recurring features of every North American summer. Until that long-term dynamic is fully resolved, you do not need to rely on speculation or sensational headlines to know which way this crisis is moving. Watch 3 specific, verifiable indicators over the coming week. First, check whether the Canadian Hurricane Centre and Environment and Climate Change Canada issue official advisories confirming that atmospheric dew points across southern Ontario and Quebec have stabilized below 16 degrees Celsius, signaling the return of true nocturnal cooling. Second, monitor whether streamflow levels at International Joint Commission gauging stations along transboundary river basins show a sustained recovery above 20th percentile historical baselines. Third, watch whether provincial health authorities report a decline in excess mortality figures back to seasonal statistical norms. Until those 3 measurable conditions are met, the situation remains locked in an active compounding crisis. Physiological debt in millions of bodies accumulates, structural strain on our winter-adapted energy grid builds, and water reserves supporting Western agriculture continue to deplete. Afternoon records tell us how extreme a single day can feel, but overnight data reveals how much time our infrastructure and our bodies actually have left before the system gives out. The daytime peak makes headlines, but the night determines who survives. Leave a comment right now telling me where in Canada or North America you are watching from and what your overnight temperatures have been this week. Subscribe to stay informed as this atmospheric pattern continues.